image compression, lossless information preserving, low compression ratios, lossy information loss, high compression ratios, trade-off information loss versus compression ratio. Compression ratio, dataset 1 image, N1 carrying units, example bits, compression, dataset 2 compressed image, N2 carrying units, example bits, compression ratio CR equal to N1 divided by N2. Relevant data redundancy, RD equal to 1 minus 1 by CR. Example, if CR equal to 10 by 1, then RD equal to 1 minus 1 by 10 equal to 0.9. 90% of the data in data set 1 is redundant. If N2 equal to N1, then CR equal to 1, RD equal to 0. If N2 is less than N, then CR up to infinity, RD up to 1. Type of data redundancy, coding redundancy, interpixel redundancy, psycho-visual redundancy. Data compression attempts to reduce one or more of these redundancy types. Coding redundancy. Coding redundancy results from employing inefficient coding schemes. Code a list of symbols, letters, numbers, bits, etc. Example, binary code symbols 0, 1, length equal to 3. So 0, 0, 0, 1, 0, 0, 1, 2, 0, 1, 0, 3, 0, 1, 1, 4, 1, 0, 0, 5, 1, 0, 1, 6, 1, 1, 0, 7, 1, 1, 1. Code word. A sequence of symbols used to represent information. Example, gray levels. Code word length. Number of symbols in a code word could be a fixed or variable. Coding redundancy. To compare the efficiency of different coding schemes, we can compute the average number of symbols, L average per code word. Example, N into M, N cross M image, N cross M image, RK, kth gray level, I of RK, number of bits for RK, P of RK, probability of RK. Average number of bits, L average equal to E of I of RK equal to summation over K equal to 0 to L minus 1, L of RK, P of RK. E of X equal to summation over X, XP of X, capital X equal to small x. Average image size, NML average. Coding redundancy example. Case 1, I of 1 of RK equal to fixed length. RK PR of RK code 1, I1 of I1 of RK. For example, R0 is 0. Here PR of RK is 0.1. This is the fixed length. So 0, 0, 0. Here I1 RK is the 3. All are 3. Here R1 1 by 7, 2 by 7, 3 by 7, 4 by 7, 5 by 7, 6 by 7, 1. For this one, 0.02 PR of RK. Code 111. I1 of RK 3. Here like this, from 1 by 7 to 6 by 7. That is R1 to R6. Here 0.25 to 0.3. 0.03. Here 0 in code 001 to 110. 3 all are 3. L1 of RK all are 3. Assume an image with L equal to 8. L equal to 8. Assume L of RK equal to 3. L average equal to summation over k equal to 0 to 7, 3 p of rk equal to 3 summation over k equal to 0 to 7, p of rk equal to 3 bits. Average image size 3 mm. Case 2 coding redundancy example continued. Case 2 L of rk equal to variable length. Table variable length coding example. rk PR of rk code 1, L1 of rk code 2, L2 of rk. R0 equal to 0, 0 PR of rk 0.0, 0.19 code 1 00 L1 rk 3 code 2 2 11 L2 rk 2 like this up to 1 1 by 7 in rk 0 1 by 7 2 by 7 3 by 7 4 by 7 5 by 7 6 by 7 1 PR of rk 0.19 to 0.02. Here like this code 1 same like before last slide 000 111 up to. Here L1 of rk all are 3. In code 2 1101 10 001 40 4 times 0 1 5 times 0 1 6 times all are 0. Here L2 of rk 2 for 2 first 3 2 then 3 4 5 then 6 6. L average of equal to summation over k equal to 0 to 7. L of rk p of rk equal to 2.7 bits. Average image size 2.7 nanometer. CR equal to 3 by 2 by 7. 1 by 1 dot 1.11 about 10 percentage. RD equal to 1 minus 1 divided by 1.177 equal to 0.099. Average image size 2.7 nm. Interpixel redundancy. Interpixel redundancy results from pixel correlations. That is, a pixel value can be reasonably predicted by its neighbors. For this image histogram autocorrelation, f of x 0, f of x o g of x equal to integral over minus infinity plus infinity f of x g of x plus a into dA. Autocorrelation f of x equal to g of x. Here histogram. In this histogram, this is for this figure. This is for this figure. This is for this figure. This one is here. Okay, interpixel redundancy example. To reduce interpixel redundancy, some transformation typically applied on the data. Interpixel redundancy example. To reduce interpixel redundancy, some transformation is typically applied on the data. Original. This is the original. Threshold. The binary image. This is the binary image. For this original, this is the threshold. Threshold 111 000 111 000. Threshold. This threshold. Psychovisual redundancy. The human eye is more sensitive to the lower frequencies than the higher frequency in the visual spectrum. In the lower frequency, more sensitive. In higher frequency, less sensitive in visual spectrum. For human eye. Idea. Describe data that is especially insignificant. Example. Example condensation. 256 gray levels. 16 gray levels. 16 gray levels plus random noise. that is add a small pseudo random number to each pixel prior to quantization. Here 256 is better than this 16 Curie. 16 Curie levels randomness. Add a small pseudo random number to each pixel prior to quantization. Data number of information. Data and information are not synonymous terms. Data is means by which information is conveyed. The same information can be represented by different amount of data. Data information example. Example 1. This is the example. Your wife Helen will meet you at Logan Airport in Boston at 5 minutes past 6 p.m. tomorrow night. Your wife will meet you at Logan Airport at 5 minutes past 6 p.m. tomorrow night. Helen will meet you at Logan at 6 p.m. tomorrow night. Reduce the amount of data while preserving as much information as possible. Uh, what is the minimum amount of data that is sufficient to describe completely an image without loss of information? We know how to measure the amount of data in an image, but how do we measure the information content of an image? Measuring information, we assume that information is generated by a probabilities process. Associate information with probabilities. A random even E with probability P of E contains I of E equal to log into 1 by P of E equal to minus log P of E units of information. Note I of E equal to 0 when P of E equal to 1. How much information does a pixel contain? Suppose that the gray level values are generated by a random process, then RK contains how much information does a pixel contain. Suppose that the gray level values are generated by a random process, then RK contains I of RK equal to minus log P of RK units of information, assuming statistically independent random events. How much information does an image contain? Average information content of an image is E equal to summation over K equal to 0 to L minus 1 I of RK P of RK. Using I of RK equal to minus log to P of RK. Entropy H equal to minus K equal to 0 integral summation over K equal to 0 to L minus 1 P of RK log of P of RK. Units per pixel, bits, that is bits per pixel. Redundancy data versus information. R equal to L average minus H. L average equal to E of L of RK equal to summation over K equal to 0 to L minus 1 L into RK P into RK. Note, if L average equal to H, then R equal to 0. That is no redundancy. Entropy estimation. It is not easy to estimate H reliably. It is not easy to estimate H reliably. Image here. Gray level 2195, 169, 243. Count probability 12, 4, 4, 12, 3 by 8, 1 by 8, 1 by 8, 3 by 8. Entropy estimation, the first order estimate of H. H equal to minus summation of K equal to 0 to 3 P of RK log P of RK equal to 1.81 bits per pixel. What is the redundancy? R equal to L average minus H, where L average equal to 8 bits per pixel.